Well, thank you everyone so much for joining another Balerion Space Ventures podcast. It's June 29th, and today I'm joined with Perttu Yli-Opas of Aurora Propulsion. This is a in-space propulsion company that's making propulsion systems that are some of the smallest in the world, down to the size of a matchbox. Really excited to jump into this. Perttu, thank you so much for joining us.
Yeah, thanks for having me.
So I want to get things kicked off with, what's that high level pitch you have for, why is this technology so unique and important to space right now?
Yeah, the let's say environment in space is actually quite rapidly shifting over the previous last few years and also upcoming few years. And the biggest change is basically in the mobility, because there is an increasing number of satellites in orbit, which means that you need to be increasingly mobile, both in getting to your target orbit, but also maneuvering for collision avoidance, but also for other purposes such as proximity operations and other more complex mission scenarios. And with this increase in need for mobility also comes an increase in need for um, the adaptability of propulsion systems. And that's what we are really targeting. And our approach, how we've approached the problem is that we've basically developed the smallest propulsion thruster there is, which allows us to actually place them on any side of the satellite in multiples, both in redundant and non-redundant configurations, providing a variety of different capabilities, all utilizing the single water-based resistor-jet thruster technology that we have developed over the last few years.
Got it. And tell me about your background. You started in Finland. What was that aha moment behind Aurora? What problem looked so obvious to you, but seemed underappreciated by this market?
Yeah, absolutely. So the kind of idea where the whole thing started from was from a university project where we were developing a hybrid rocket engine. And I was really looking into like what would be the commercial use case for such engines, and ended up not really finding any. And instead I started mapping the field of what is it actually that the market requires, and I found my co-founder from Nokia. He was working at 5G networks being taken into space context, and he got super interested in what we were doing at the university, other university. And essentially, we started looking at what is the market trend currently, and this was back in 2018. Um, the market trend was clearly going to smaller satellites, going from large satellites to small sats, but also all the way to CubeSats. But there were no viable propulsion systems for the CubeSat form factor. So it was very clear that CubeSats cannot keep flying without any propulsion systems. There will be a huge, huge need for such technology. And in Finland, we have very, very good expertise in making miniature systems. So basically, everyone knows how Nokia used to be the smart, like pre-smartphone technology everywhere, and famous for being very small and very durable. And actually, it's partially the same people that we are utilizing for our technologies as well, because we have a world-class school of watchmaking in Finland that we have been hiring quite a few people from. Those people are actually the people that know how to build things very, very small, how to manufacture them, but also how to design them. And that's basically the expertise that we've been able to utilize to develop this world's smallest technology. And really, the bottom line was getting to that smaller satellite size market, which just hasn't been covered by any propulsion systems. Now, then the kind of upcoming trend from that point, which is now very much like reality today is that the CubeSat as a platform is used for technology demonstration. But then once you actually start doing business with your platform, you usually end up moving to multi 10 kilogram platforms, which means that 50 to 200 kilogram mass class ends up being the workhorse of most constellations that are actually starting to make money. And that actually gives a very interesting kind of trajectory for the customer relationship that we have, which is that we need to be able to supply to the CubeSat when they are flying their technology demonstrator. But then once they grow into that small sat category, we need to still be able to supply the same systems to them. So basically, we need to be very, very flexible in both the system size, but also the configurations and, for example, the quality standards utilized, because they change so much in the life cycle of our customer that we need to also adapt to that whole life cycle.
Yeah. And can you break down the core technology here? The propulsion systems, what propellant is it using? And just so we have an idea in our minds and just, plain terms, what's novel about this?
So actually, we have two core technologies.
Nice.
The main workhorse is the water resistant. So the easiest way to explain it is that it's a space kettle. So it's literally just a very, very hot metal pipe that we put some water into. The water vaporizes and the steam jets out, and that pushes the spacecraft forward. So very, very simple technology. Instead of using a chemical reaction as chemical rocket engines use to heat up the gas, that's essentially what rocket engine does, uses a chemical reaction to heat up the propellant. We use an electric heater, and the electric power heats up the propellant to actually generate the energy that is used for the propulsion. Very, very simple technology, but the difficulty comes from the miniaturization and making it actually reliable. Then we have a second technology as well, which is the plasma brake. It's also propulsion, but it's actually propellantless. So it's a tether. It's a metal wire thinner than a hair that we open from the satellite. And we charge that metal wire to minus 1000 volts. And essentially, it works as a virtual sail. So it's basically like an anchor bringing down the satellite from the orbit. So it's for deorbiting the satellite at the end of life, or for example, removing existing debris. So we can go to a piece of debris, attach one of these plasma brake devices. It opens this metallic wire, which then drops that piece of debris back into the atmosphere so that it doesn't remain as space debris.
Wow. Very cool. And where do you sit on the spectrum between propulsion, mobility, debris mitigation? And do you see those converging into one category?
Yeah, absolutely, absolutely. So essentially, the first few years we were just focusing on the technology development and the initial product development. So basically, just selling subsystems to satellite manufacturers. But now we are transitioning into a little bit more comprehensive solutions where we are combining also our technology with other technologies. For example, we launched in 23. We launched the Strider satellite, which has a combined system that has a Hall effect thruster, which is able to make very large orbital changes, and four of our thrusters, where the Hall effect thruster is actually supplied from a partner of ours, Aliena. And we are actually feeding the propellant from the same propellant system. So there's a single tank that feeds propellant to one Hall effect thruster and four of our resistor jet thrusters. That allows us to do this like multi-purpose mission profile where we are able to do larger orbital changes, but then also do local maneuvering, for example, for proximity operations scenarios in a system that is much, much simpler compared to having two complete propulsion systems on board. And essentially, that's what we are currently doing is more integrated mobility solutions, let's say. Of course, a lot of customized solutions as well for whether it's attitude control or collision avoidance or whatever the mission profile is, formation flying, for example. And then in the future, we'll be going even more into the vertical integration direction to provide even more end-to-end, basically, let's say, solutions.
Got it. And tell us about the satellites that these propulsion systems go on, like, so we can get an idea of just how big they really are, or how small they really are, and how are they changing?
Yeah.
Like several years ago, did they even have propulsion on them?
Yeah, so if we talk about CubeSats first, which is what we are currently mostly working with, they are anything from a couple of kilograms to like maybe 30 kilograms. Um, More than 90% of them still don't have any propulsion. So
Wow.
they are flying without anything. And the problem is that now the regulation is coming in both for deorbiting, but also collision avoidance. You need to be able to drop the satellite at the end of life, but also avoid collisions because there starts to be so many operational satellites in orbit that actually you might even get daily conjunction notifications when operating your satellite in the congested orbits. And this means that CubeSats are in need of simple and reliable and kind of straightforward solutions that can provide that um, regulation compliance. But of course, also more complex mission scenarios are coming up which require propulsion for the mission scenario itself. But we are especially now scaling up to that 100-kilogram class of satellites. We are scaling up the water resistor jets from 1 millinewton class to 10 millinewton class, with hopefully the first customer deliveries Q1 next year on the new scale of system, which allows us to go into especially that proximity operations type of use cases, both for the sustainable space, but also other use cases.
Got it. And when people think of space propulsion, they think of rockets, they think of, these powerful thrust systems, but that's not really the case when you're in space, is it? Um, if this thing was to be firing on Earth, about how much thrust would it give off? Like, what could it move if there was something on wheels? Could it move a box with 10 pounds on wheels, or maybe not even that? Because when you're in space, you just tap something and it goes. It's kind of like a puck on an air hockey table.
Yeah, that's exactly it. So because there's no friction in space, movement doesn't really change other than from gravity. Energy is almost perfectly conserved in space. You don't need a lot of thrust. Instead, what you do, you use that thrust for a long time for the same effect, and you can be actually much more effective with the use of propellant. In terms of what is the scale of thrust, it's very small. So 1 millinewton scale is something like it could basically push a pen on wheels, not a box on wheels, let's say. And maybe we are going to 10 times that. So it's like barely noticeable push. Like that 1 millinewton scale where we are at right now, you basically wouldn't feel it at all. The key is that you use that over long periods of time. Over a few minutes is actually enough for many, surprisingly many use cases, but up to a few hours or a couple of days in like continuous operation, basically to do whatever your satellite actually needs to do.
Got it. And the demand from this for this by customers, where's this coming from? Is it being pulled by regulation with deorbit requirements and debris mitigation, versus maybe operators just want this to optimize their fleets? Like, what's the driving factor behind the customer's demand?
It varies wildly between customers. So there's a lot of very interesting mission scenarios. For example, the mission that is right now in orbit is Wisdom, which we've done with C3S from Hungary. It's actually a 6U CubeSat, which is about to split into two in orbit. So it splits into two 3 units. And then our thrusters are being used to actually separate those. And they are testing a inter-satellite communication link. So there's a radio link directly between these two satellites. And our thrusters are being used to drive them apart for that testing. Very, very interesting use case. But it's not really something scalable. And actually, right now, most of the mission scenarios are quite unique that we work with. Of course, there's going to be some overlap, and that's our kind of main challenge to capture that overlap in the product specification so that we can address as many of those missions as possible. But the only kind of bigger trends are coming from the regulation, where suddenly certain jurisdictions, let's say, start requiring a propulsion system on every single satellite. So then they need to scramble and find something to fly. But other than that, the scenarios are very different because each of the satellites missions are very unique. Often there are multiple satellites involved with some like relative navigation requirements that need to be achieved.
Got it. And these small satellites, just a couple kilograms, what missions do they usually serve?
So on the CubeSat level, it's often the uh, technology demonstrator being like the most common use case. So you are kind of proving that whatever components you are developing for satellites are functional. Then when you actually go into business, the 50 to 200 kilogram satellite class and larger as well, um, of course, the main let's say division of different business case goes into communication, starting um, imaging, Earth observation as a topic. So imaging anything from ISAR radars to Google Maps or whatever imagery is being taken of the Earth. And then science, which can be environmental measurements of the orbit or telescopes or whatever. But in terms of most of, let's say, commercial actors. It's going to be either communication or Earth observation. And the communication can be anything from these, broadband internet to Internet of Things, very low data rate communications, but also things like quantum key distribution for quantum safe encryption systems where you need to actually transfer a quantum state to the other side of the planet. You cannot really do that on a terrestrial means. So you actually use a couple of satellites to send that quantum encryption key so that you can actually have quantum safe communications.
Wow. And the customers you have today, the core customers, are they new space startups? Are they, primes? Is it government? Who's looking to buy these right now?
Yeah, it varies wildly. So of course we are working with the European Space Agency quite a bit. So we have a few contracts with them. We have startups, we have research organizations as customers. So the profiles vary wildly, and of course the requirements and let's say practices of working vary wildly as well. But essentially, any global actors in space, be it a university building their first CubeSat as just a student project or a agency of a government on whatever level, anything is possible.
Got it. And right now, you have your propulsion systems in space. Tell us a bit about the traction and some of the milestones you've hit to date so far.
Yeah, so we've launched a total of, let me actually double check. Yeah, I believe um, 14 thrusters on four different satellites, um, with including three plasma brake systems. The plasma brake systems are pending deployment, so we haven't actually been able to yet deploy the system. So the first satellite that had the plasma brake failed on the bus side, so we never actually tried to got to actually starting the experiment. So that's kind of the biggest upcoming milestone for the plasma brake side. On the thruster side, we've fired the thrusters in space, so we have a little bit of data from orbit, and we've delivered quite a few upcoming flight models to customers already. So expecting quite a bit more data in the near future.
Got it. And the satellite market today, it seems it's growing exponentially. It's growing incredibly fast. Most of it is Starlink, and more space tech companies keep popping up and wanting to get access to space. And we've sort of learned that maybe SpaceX, the transporter missions aren't really worth their time. So there's this backlog of all these other systems that are trying to get into space. Um, and maybe, they can't get there yet, or they need to find another way up. Where do you see this ecosystem going, the next few years of what we can expect space to be different in terms of all the satellites up there?
That's a very good question. Of course, there is a large number of uh, launch providers popping up globally that are basically filling that need for more flexible launch solutions. Thus far, most companies have been happy to launch at a lower cost with SpaceX rather than trying to pay more for a specific orbit because typical mission scenarios can work with a bit more flexible orbits. But then, yeah, this question of how the SpaceX, let's say, availability evolves already, it's actually very difficult to get SpaceX launches. You need to book them multiple years in advance, and that is a big bottleneck already. So there's definitely a big push from that side in the European side to develop capability locally to have a little bit more flexibility on the launches. But right now, most players are still happier with the lower cost of SpaceX because uh, they don't see that much benefit from the let's say more custom launch opportunities. But yeah, of course, the market is changing. There are bigger forces at play that may affect the availability of the launches in the first place. So of course, Europe is looking at more, let's say, local supply chain end to end, which makes sense in the current geopolitical situation. But I would be happier to see a little bit more global cooperation on that front as well, because if you look at the industry as a whole, it makes absolutely no sense to have 50 companies developing small large vehicles because there's just no market for that many. So there's going to be some changes in that field. A few of them will be alive in 5 to 10 years. Most of them will not because there will not be a big enough um, demand since it's easier to scale up an existing functional launch system than develop a new one. So once the first few have gotten to routine operations and are able to actually start scaling their operations, they will feel the market that there is to fill.
Got it. And yeah, I'm just thinking of these systems in space. How long can they stay up there? How many thrusts and can they give to these small sats? Can they constantly be maneuverable? Are they just having this propulsion system on board in case they need to, avoid debris or deorbit? What are the capabilities once one of these small satellites has your propulsion system on board?
Yeah, so we've aimed at a middle point in terms of the performance of thrust versus specific impulse. So what it means that you can have a chemical system that provides a huge thrust for a very short time. Or you can have electric propulsion system that provides very little thrust for a very long time. If you want to operate your thruster continuously, you go for an electric propulsion system and you can operate it for months in total. However, that also means that if you want to do a significant change, you need to operate it for months because the thrust is so small. And if you go to chemical, the total impulse is a little bit more limited than on the electric propulsion system. But actually, a larger problem is really the compatibility of the propellants and a lot of other complexity that goes into the chemicals, as well as precision. Because when you are generating easily 1,000 times more thrust than we are generating, which is already 100 times more than the electric propulsion is, you cannot control it very finely. You can make a large burn and quit it, but you cannot do any fine tuning. So where we are located is a middle ground where we are able to make relatively good-sized orbital maneuvers in days rather than months. But we are very, very finely tunable. So this is why the technology works especially well for these proximity operations where you need some hours of thrusting relatively continuously with very precise adjustments. That's our kind of sweet point. But of course, then we combine, as I explained, that we already have that Hall effect thruster, so we can provide very, very high total impulse combined with this medium range. We are also looking at the chemical end, so we can also partner up with a company that does chemical propulsion. So you have the higher thrust for larger, shorter time maneuvers, and then you have the precision from our systems. So it is definitely a technology that um, in many scenarios will be used in the context of other technologies to perform the whole mission. But in short, the mission duration, there's no inherent limitation. It depends on what you use it for, how much water propellant you need. The more you need, the bigger tank we put. So we just size it for your mission needs, and whether it's going to be 2 or 3 years on these smaller satellites, but up to 5 years we can easily handle.
Yeah. Now, you guys founded in Finland, not a spot where you see a lot in the space community, and you've been there, for a few years now. What's the ecosystem been like in the space tech community throughout the years in Finland? Like, how has that changed, and where's it at right now?
Yeah, so the Finnish ecosystem was quite small when we founded it 8 years ago. Um, of course, ISI had started growing, but it wasn't really known globally yet. It was known locally. But traditionally, Finland hasn't really developed satellites. The first Finnish satellite was actually launched in 2016. Um, we have been developing instruments. For example, on Mars, there's a few weather instruments from the Finnish Meteorological Institute. So there's a little bit of like industry that has been working on European Space Agency missions, but this let's say new aspect of actually building satellites and components as commercial startups basically is quite recent. And that means that in these 8 years, the change is huge. It's absolutely huge. So we went from us launching, I think, was it like the fourth satellite, Finnish satellite ever as our first satellite. Now there's more than 40 Finnish satellites. ISI obviously is a huge player with over 10 billion valuation at the moment, which is ridiculous. They have been growing faster than you could ever expect. And of course, that is pulling a lot of workforce into Finland as well. Reorbit, also on the same campus as we and ISI also, or Reorbit and Kuva, both are actually growing quite a bit as well. So there's a growing industry and things are looking very good. The finding of talent has become much easier because the first years it was very difficult to find talent that is actually experienced in the space industry. But now that situation has changed very significantly within the Finnish ecosystem.
Got it. And being a space company in Europe versus the United States, what would you say is a lot harder and what would you say is a lot easier?
Yeah, that's a good question. So definitely in the US, the public funding from DoD is going to be much more flexible and easier to access. That's one of the bigger factors. It's very differently structured. The money is a little bit bigger. But then in Finland, especially, there's relatively easy to access money from Business Finland, which is the Finnish government funding agency, which essentially matches any investments that you put into R&D. So all R&D work, they'll cover half of the cost. That's a huge boost. Um, Then, of course, there's European Space Agency and EU funding that you can access. But of course, in general, the biggest difference would be that typically the amount of funding you are easily accessing in Europe is going to be maybe half or a third or a quarter of the US funding. But with the government support and also with salary levels being much more modest for the top employees, there's actually a huge difference. Even though the median salaries are not that different, the salaries of high-performing employees are easily 5 times larger in the US than in Finland. So actually, the expenses are also quite a bit lower. So it's hard to say because like the whole ecosystem is very different. The way you act in the local ecosystem is very different. Typically, the US startups are starting bigger and moving faster, but that doesn't mean that you cannot move fast in Finland, as proven by ISA, of course.
Yeah. Do you see Europe shifting to, you know, beginning to start investing more capital, both on the government and the private side of things? We've seen a dramatic shift in, the investor mindset in the United States, especially since the SpaceX IPO. Is there, something happening in Europe that's just the trailblazer, that's changing everyone's mind, that's leading the ecosystem of space tech to move a lot faster and get funding more easy. Um, I know there's not a ton of launch providers, but it is in the works. What do you think is some of the brightest hopes Europe has right now for really helping expedite and grow the space ecosystem?
The industry in Europe is changing a lot in the last year, let's say, um, largely with the introduction of, let's say, defense side into the EU and ESA, because both ESA and EU have been like strictly non-military side, but that has changed. And now there's much more collaboration between defense industries and the other public sectors, and that has been really acknowledged. And the structure of the funding has already shifted quite a bit. And of course, there's things like European Defence Fund, which is relatively new instrument for funding as well, which is making a shift. But of course, the actual growth comes from the companies. There's a huge amount of companies that are looking very promising in basically all sides of the space industry. Um, I would say that the one of the differences between the US and Europe is that US tends to look at like single large growth factors. In Europe, it is more of a local economy and networks. It has both its good and its bad sides. But of course, yeah, I mean, ISA is going to be one of the good examples of how a company can grow very rapidly and keep growing, like not just becoming a unicorn, but then going 10x from that and maintaining that growth with fully European and in this case fully Finnish technology.
Yeah. And for a company like yours, the systems you're building they're not huge. They're quite small. So scaling up, very hard. If you had to scale up to 10x, you had 10x the amount of orders for next year, like where do the bottlenecks come in? Like what's going to be the hard thing you're going to have to figure out?
Um, 10x is not that difficult yet.
Okay.
100x starts to introduce bottlenecks, but we've built our company from day one for series production. So actually, right now, with like around 10 products a year being developed, we have like internal processes for production that are way too heavy for this volume because we have already prepared for that 100 unit volume. And we are basically ready to jump into that as soon as we get the funding and the customers to jump into it. Of course, hiring is going to be the thing that brings like 3 to 6 months of delay before we get new people started. But we are like after that we are ready to go 10x. Then after that, of course, if we need to go 100x, then we need to start looking at a little bit more facilities and so on. But since the actual volumes are still so low, it's like there's surprisingly little investment that goes into the production itself. So the 10x we can get with like a few million euros of investment into the production system. Then into 100x, it's really just maybe 20 million into the production facility, and we can get there. So it's um, quite straightforward because we have taken it into account in the design from day one. So basically, we've always looked at the manufacturability of the components. Where do we procure them? Do we build them internally? What's scalable so that we can just place orders for larger amounts and start going there? So yeah, the bottlenecks, of course, there's gonna be surprises. It's never that straightforward when you start doing it, but it's not a big threat, let's say.
And with your systems being so small, do you usually put one of these on just a small satellite? Would there be any use case where maybe you put, a handful or a dozen onto a small satellite? What kind of use case would that be?
So on the wisdom system, we already have four thrusters. So yeah, it's
Okay.
very much common that you
Okay.
have multiple. There's a few different reasons. Redundancy is one. In general, propulsion systems are not very reliable. Even when you make a very reliable system, it's gonna be maybe 90% reliable, which means that you want to put two of them, and then your reliability is 99%, depending on the use case. Um, but then uh, basically looking at the proximity operations, for example, it's one system, but it consists of 12 thrusters. They are interconnected into one tank. They might have a couple of tanks, so it's kind of a comprehensive solution that we are selling that includes a large number of thruster for whatever you need to do. But absolutely, like it's not just one thruster per satellite.
And are there any things coming to low Earth orbit that are, quite interesting when it comes to maneuverability? We see the communications, we see Earth observation, and, component testing. It's all pretty standard. But then you start seeing things like in space manufacturing, you start seeing things like, space defense and military applications, defense applications. Looking forward in the future, are you guys positioned very well for one of these upcoming markets that maybe isn't huge right now, but will be?
Absolutely. So of course, if you want to look at military side, the number one thing that they care about is being able to move. You are sitting duck otherwise, um, and their requirements for that movement are very different from the traditional space industry because their let's say perspective on of analyzing the whole mission is completely different. And let's say collision avoidance gets a new meaning when you get into that level. Um, but so that's the obvious angle. What comes to some of the in-space manufacturing and let's say power generation data centers, um, we won't be acting in the like multi-ton spacecraft scale. We are looking at small spacecraft, so constellations where like up to few 100 kilogram transporters are used in larger volumes. That's our space. So it depends if you are having a constellation of let's say computing platforms. We definitely will play a role there. If you want to make a one huge space station which does everything in a centralized manner, then we probably won't have a role there.
You know, and yeah, just thinking about more into the future with things like, maneuverability for military applications in space data centers. Do you think the right now you're building for the industry that exists today, or are you more aligned with providing systems for that future industry? And there's kind of this inflection point that you're hitting to where not only do you offer, a desirable product, but now a lot of people need their product for these new systems or regulations change and you need debris controls. propulsion systems, things like that.
Yeah, absolutely. We are definitely looking forward. So, for example, the plasma brake for the orbiting, when we decided to start developing it in 2018, there was no market for it. But we saw that within about 5 years, there starts to be the first regulation that will actually require it. 5 years later, we get the US regulation for the orbiting within 5 years. So actually, we were spot on that regulation. Collision avoidance has been taking a bit longer than we expected. That has come into force in certain countries, for example, France. EU space law is moving very, very slowly, but that's something that we started developing in 21. Um, Also looking like a few years ahead. Now we are looking at what is, let's say, 5 years from now, what's the actual reality, what is the maneuverability that is required, and yeah, that's absolutely the context where we are working. That the aiming point is about 5 years because it takes about 5 years to first develop the technology, demonstrate it, and actually be able to commercially deliver it.
Yeah. And what what's some of the reasons that a new propulsion system can take a long time, like from first conversation to having in space flight heritage? What's going on in between when you're having something as new as not just a component, but an actual propulsion system? You can't just put it on a bus and test it in there. You got to be able to control satellites with this and move them.
It's not a single big thing, it's millions of little things.
Okay.
And it's just ridiculous how many things there are. Compared to other satellite subsystems, the difference is that other subsystems are basically just electronics and software. So the core expertise of your company that actually manufactures them is just going to be on the electronics and software sides. But when you look at propulsion, you need to actually start looking, well, propulsion itself is a competency as well. You need to start looking at mechanics in a much more high fidelity. Of course, all satellites need some mechanical design, but typically the propulsion system's mechanical design is much, much more complex. You start to look at material properties, a lot of chemistry. Even if you don't have a chemical propulsion system, there's a large amount of chemistry. The introduction of fluids and tanks and moving components, extremely complex. So there's just a million different things that first broaden your core expertise that you need to handle. And basically, every single interface between the two different core expertises is a potential place for problems. So when you go from three core expertises to six core expertises, you go exponentially larger in terms of potential problems and like the solutions that you need to develop. So it just takes years and years to first develop the core technology for the propulsion. And once you have the technology, you cannot call that a product because it's a thruster that works in a vacuum chamber. Then you need to make it into a product, which means that you actually need to figure out what is the configuration. And we are selling like tens of different configurations. So it's not a simple question. How do you install it into the satellite? What are the other components needed? What are the interfaces to the customer? Developing those, testing those, um, and then actually getting the flight, which is typically anyways going to be delayed. Like our first satellite was delayed by 1.5 years by the launch providers. First Momentus, with a lot of history there, what happened, and then with a reprocured launch from Rocket Lab, which was also more than 6 months delayed from the original launch date. So that plagues the whole industry. Everything is slow in terms of IODs because you cannot trust that you actually can fly the technology once it's ready. It easily takes at least a year, often even 2 years before it's actually tested in orbit.
Wow. So yeah, it seems very complex when you're trying to grow your company right now. Are you trying to, you know, build new systems, or are you really trying to sell what you've created and worked out? You talked about maybe scaling up and having it for larger, vehicles. Uh, Other than manufacturing, sales, things like that, the R&D in your company, like what are you focusing on to improve on new systems?
Yeah, so what we've developed is the modular architecture where we can install the thrusters on different sides of the satellite for whatever use case. And essentially, what it consists of is the thruster itself, the piping, valves, the tank, the control electronics. It's a modular architecture which we can reconfigure for different use cases. Every use case is a bit easier to implement than the previous. And now, in terms of like new R&D, right now we are developing the 10 times more powerful thruster. And the benefit here is that it uses the same modular architecture. It's only the thruster tip that changes. Some tweaks to electronics needed, but very, very little, which means that actually in terms of the product, more than 90% of the components will be identical, even though we 10x our power. So we have a modular architecture that we are now scaling up to different use cases and to larger volumes. So basically, I mean, yeah, we've done that for 8 years. It took a long time, but now we are to the level that we can deliver it even at very, very short time frames. We can actually get an order in and deliver flight models within 4 months if there's no customization, or even with a small bit of customization, 6 to 8 months from order, which is basically unheard of in the industry. Typically, the lead times are like 1.5 years around that. And especially now within the last half a year, the customers' expectations and requirements for the delivery schedule of the products has dropped to like 1/3 of what it was. There's a huge shift in the industry right now. And we've actually seen a big spike in our orders just because we are one of the only ones that are able to deliver in very short time scale.
On it. And what's something that you wish investors would ask you about, but they almost never do? Like, what's something that someone who hears about this, they think they understand, but they're missing a big picture, and you wish they would ask an important question that goes under the radar?
Well, that's a good one for sure. So I would say that one of the interesting kind of under the radar things is how do you develop things and what's your processes like what's your approach to quality, and there's a big gap between new space that develops something that might work and old space that develops something that works but takes 10 times longer and is 100 times more expensive. Um, and while SpaceX is maybe still the only uh, really kind of party that has cracked the equation of making fast prototyping in a way that is actually valuable to the design. That's a very difficult thing to find, and that's been kind of one of our um, let's say guiding forces of how we've developed the company internally is that we try to find that middle ground where we have formalized processes, but we are not following the old space industry standards. We are not looking at those processes from anywhere else. We are adapting some of them that we actually see have a concrete impact on the product, typically simplified, and forget everything else. And we've internally developed a set of processes that actually allows us to very effectively maintain the quality of our R&D and also production. Production side is still under development. That's one of the bigger things that we are actually fundraising for at the moment is the setup of production, which includes the processes for the production, of course. And I would say that we are much more formalized than most startups in how we do things. Um, but still, our delivery timelines and also expense profile is the same as the other startups, which is much better than I was expecting when we started off. Like it's turned out really effective where we are actually really agile while still having relatively comprehensive set of internal processes.
Well, Very nice. I like that. Well, Pietro, this has been fantastic conversation. If there's anyone who's listening to this recording and you wanted them to walk away with one big takeaway from what we've discussed, what would you want that to be?
Um, I would say that even though we didn't directly discuss this yet, but there's a transformation in the industry where the new space industry is becoming um, kind of the default way of doing things. It will look different than the new space industry has looked thus far. But actually, old space needs to also adapt to that. Old space will not be able to maintain its ways of working for most of the activities that they are working. These two worlds that do function very differently currently will be approaching each other. And the question is, who will survive in this market? Is those that are not very clearly either, but are able to actually find a common ground and um, an approach to quality that is actually scalable to larger production volumes, which old space absolutely is not.
Well said. Well, I want to thank you so much for taking the time to join us today. This has been a fantastic conversation, and I'm very excited to see where Aurora goes in the future. I think we're going to see a lot more of this. You've sold me.
I think, yeah, thank you very much. This was a pleasure.
All right. Well, take care and hope to chat again real soon. Thanks.
Awesome. Thanks.